Welcome to Tech Teach.
So here the different types of line coding schemes. So there are like basically 5 different line coding schemes are there. So one is called unipolar, next is polar, then bipolar, then multi-level and multi-transition. One by one we will be going with each one. So unipolar, in unipolar the type of line coding technique is there, that is called the NRZ, that is non-return to zero. Similarly in polar, polar can be of NRZ type or RJ, or it can be biphase. So in biphase we will be studying the Manchester and differential Manchester, NRZ and RJ. In bipolar, again this is biphase, this is bipolar. So in bipolar we will be studying AMI and pseudo ternary. In multi-level we will see 2B1Q, 8B60 and likewise. And in multi-transition it is MLT3. So these are the different categories. So these are the different categories. In that categories, these are the encoding techniques that are available in this category. Okay. So what these categories are there, we will just go one by one. So it is, the first one is unipolar NRZ scheme. So in case of unipolar, its meaning is like, unipolar means all the waveforms that will be there, that will be in one side only. So unipolar means it will be, you can just write here. So unipolar. So unipolar means all signal levels are on one side of the time axis. That is either above or below. So in unipolar, the waveform that will be there, or the signal that will be there, so signal will be either in the positive side, the whole signal will be in the positive side only, or it could be in negative side. That means, or unipolar can be like a waveform will be there. Okay, so that will be a waveform will be having amplitude, this is 0, and now it will be represented by minus V. Okay, so if it is representing 1, so for 1 it can be negative. Okay, for 0 it is could be positive, and whenever there will be 1 it will be negative, and then whenever it will be 0 it will be 0. So first of all, unipolar means it will be only one side of the time axis, either positive V or negative V. Unipolar, so it could be either positive side or negative side. One more thing is like, if it is 1 or 0, so 1 can be included as level 1 or level high, or level low. This 0 can be again level high or level low. Low means 0 here. So its meaning is like, here in the first case, here if we want to encode, basically digital signal is 1 0 1 1 0. We want to encode this one. So it is unipolar. So either we will be using the positive side or the negative side. So suppose it is using positive side, then 1 is encoded as high, then 0 is encoded as low. Okay, low means 0 level. Okay, so then again 1 is there, then a high level V plus V low level. So this is the signal, basically this is the encoded signal. So signal will be having a value likewise. Okay, so this will be transmitted, this is the digital signal. Okay, so this is done in unipolar NRZ. So here NRZ, what is the meaning of NRZ? Is meaning like non-return to 0. Non-return to 0 in the sense, suppose this is the 1. Okay, So this is one bit, one data element. So in this one data element, level of the signal will be constant. It will not be changing. It will not be returning to zero. It is, if it is positive, then it will be positive. If it is zero, it will be zero only. It will not be returning to zero. It will not be going to zero. This is, once we will be seeing the next one, we will be able to easily understand like what is the return to zero means. Okay. So this is how the unipolar NRZ scheme is there. That will be basically converting a digital data to a digital signal. So in terms of the parameters that we have just gone through, so parameters is like bandwidth, baseline, wandering, and complexity, and DC components. These four we will just go through. Okay, this is like if we talk about the bandwidth. So if we talk about the bandwidth here, so in terms of here, the bandwidth is like given by, if it is a digital signal, first of all, it is a non-periodic. If a non-periodic is there, then its bandwidth will be like a continuous one. So similar here, its bandwidth will be given by like starting with 0, mostly it is on the likewise going up to infinity. Okay, or if it is practical one, it will be shortly terminated. Okay. So this is basically the frequency, and this is the amplitude. Its bandwidth will be likewise. So it is like most of the bandwidth is near to the zero frequency. So it should not be like that. It should not be like most of the bandwidth is near to the zero. It should be between 0 and 1. It should be distributed equally, or it should be ideally distributed likewise, equally distributed likewise. Okay, or there should be a uniform pattern, but it's not should be at the here. So most of the amplitude is near to the 0 likewise. Okay, this is the case in case of bandwidth. Next parameter was baseline wandering. So baseline wandering will be there if there is no DC component. So but here if we take the average will be like this. So this will be the average value. So average value, there is an average value, or we can call it like DC value. So DC value means its average value is how much going beyond 0. If it is near to 0 means DC 0 is there. If DC is beyond 0 means it is higher to this, so it will be having non-zero DC component. If it is non-zero DC component, that means it is not a perfect line encoding technique. And also in terms of the next parameter like bandwidth and wandering and DC component. So DC component we have seen also like DC component. Yeah, but in terms of complexity, it is very easy to implement. So it is like if it is 1, make it high. If it is 0, make it 0. So it is easy to implement in terms of the complexity if we talk about. So it is less complex, we can see. Is normalized power is basically given by like for the 0 transmitting, it is having no power. It is 1 transmitting, it is having V power. So average power for one cycle if we call about, so it will be like average power we will be having half of V square. So unipolar either it should be either positive side or negative side. NRZ, it will not be returning in between the data element transmitter. If it is 1 is transmitted, it will be constant to either high or low only. If it is 0 is transmitted, it will be constant at that level. So that will be NRZ. The next we will see is polar. So what is the meaning of polar? Polar means it will be having both positive and negative. Both component will be there here. So that's why it is called polar. So you can just see here polar. Polar is of 2 types. In polar, we are having 3 different techniques. So like NRZ, RZ, and then one is like Biphase. 3 techniques are there in polar. NRZ is like non-returning to 0. It is not returning to 0. So whatever is there, if it is 0, so if it is represented by high, so it will be high only. If it is 1 is represented by negative value, it will be negative only, constant. It will not be going in between. There will be no transition in between the signal. So that's why NRZ. So NRZ is there, but it is polar. Polar in the sense it will be having the positive as well as the negative part. So one either positive or negative can be represented as 0 or 1. So in this case, it is representing 0. 0 in the sense 0 bit is represented by high value. 1 is represented by negative value. So whenever there will be 0, it will be high. 0 high. 1 means negative. Negative side it will be there. 1 negative side. 1 negative side. 0. So likewise, suppose there is 0, 1, 1, 0 is there. Suppose this is the case. So how we will be representing it? So if it is 0, so 0 can be either positive or negative. Suppose we are considering 0 as a positive, so it will be positive. Then we are having 1, so 1 will be negative. then again 1 is there, so again we will be negative. So this is 0, this is 1, then again 1, then again 0, means we will be going to the positive side. So this is 0. So this is how the encoding will be done. This is called NRZ L. L here represents basically the level. So level in the sense we are having NRZ, but NRZ is being basically considered in terms of levels, either it is positive level or negative level. So here L stands for level, that is level of the voltage that is defining the bit value. So if it is positive level, so positive level is basically in this case 0 is being defined by positive level, 1 is defined by the negative level. That means here the level is going to define the bit value. Okay, so that will be the NRZ L. Next is NRZ I. So I stands for invert. I stands for invert. So what is the meaning of invert here is, so there will be a change or lack of change. It will be changing or not changing these values or these levels basically. So these levels will be changing or not changing based on the value of bit. So value of bit is there, suppose. Okay, so if it is 0, so by default the first starting is from the positive side, because 0 is labeled as positive. So starting with positive, but in NRZ inversion here is like when the inversion will be taking place, if the next bit is 1, if the next bit is 1, then there will be an inversion. If there is no next bit is not 1, that is next bit is 0, no inversion will be taking place. So this is the case. Okay, here first bit is 0, so 0 will be similar to the NRZ L, positive value. Okay, so now at this point we need to think of what is the next bit. So next bit is 1. So if it is next bit is 1, so for next bit is 1, we need to do the inversion. Inversion means it was positive, then it should be inverted to negative. Okay, so inversion will be done if there is a 1. Now at this point again it will be checking what is the next bit. So here next bit is 0. So if next bit is 0, no inversion. No inversion means it is negative, so it will keep on negative only. Again at this point it will check whether next bit is 0 or not. If next bit is 0, then again it will be having no inversion, no change will be there, no inversion. So whatever the negative is coming out, the negative will continue. At this point again it will be checking the next bit. So next bit is 1. If next bit is 1, that means there will be an inversion. So inversion is done. So it was positive and negative. Next inversion means now negative. If it is negative, now inverted with positive will be there. So now it is positive. Again at this point it will keep on checking the next bit. So next bit is again 1. So it will again invert. Again at this point it will check the next bit. So next bit is 1. So it will again invert. At this point it will check the next bit is 0. So there is no inversion. It will keep on constant, the positive side only. So this is the NRZ I. I stands for inversion. So whenever there will be an next bit is 1, there will be inversion taking place. If next bit is 0, no inversion will be taking place. So these white circles are indicating like there is no inversion. These black circles are basically indicating there is a inversion taking place. So whenever there will be an inversion, so there will be change in level, voltage level change will be there. So it is positive, so it will be negative. So if this is black, that means there is an inversion. So from negative to positive. Again it is inversion, so from positive to negative. If again inversion, from positive to negative likewise. This is basics about NRZ L and NRZ I schemes. So bandwidth is given here, like the maximum is going to be high, or at 0 frequency the maximum is 1. Okay, so mostly the maximum bandwidth is coming out to be 0. So it is again not suitable for practical applications. So we should not be using that for practical applications. And here R is equals to 1 given. So 1 bit is transmitted for 1 signal level. So this is R is equals to 1. As average, that is signal rate or the baud rate is average baud rate is n/2. We are using the signal rate less than the bit rate, means it is better. So the signal rate should be less, means whatever the signals we are transmitting, that should be less to represent the total number of data that we are transmitting basically. Okay, so here the signal rate is as average signal rate is n/2 basically here given. So next we will see RZ. In NRZ L, the level of voltage determines the value of. In NRZ I, the inversion or lack of inversion determines the value of bit. Whether there is inversion happening or not. If there is no inversion, so how we will be identifying? So if it is 0 means starting with 0. If it is inversion means next bit is 1. So while encoding, we need to think like what is the next bit. But while decoding, we will just see, we thinking like when there is inversion means there is a 1 basically. If there is inversion, next bit is 1. Then after that, there is no inversion means next bit is 0. No inversion, next bit is 0. No inversion, next bit is likewise. So inversion, next bit is 1. Inversion, next bit is 1. That's how we will be able to decode it. NRZ L and I both have average signal rate n by 2 baud. Both have DC component problem. So if DC component problem means this DC component is not 0, then there will be a problem of DC component that will be basically saying like there will be extra power dissipation. If there is extra DC component is there, then a signal that is constant for a long time, either positive side or negative side, then it will be resulting a high power basically. A DC problem we should be avoiding. So if DC problem is there, that means at 0 frequency there will be high power, or most of the signals will be focusing on the 0 frequency only. So if it is 0 frequency means sometimes what happen if a channel is there, if we are having a channel, if it is providing most of the power at the 0 frequency and this channel is band pass channel is there, then it will be not allowing this 0 frequency. So most of the power will not be passed through this. So if most of the power is not passed, so only the left out power, the remaining power is basically being utilized. So that will be a distorted signal will be obtained here. Okay, so that's why we need to avoid the DC component of the next one is the polar RZ. So first of all, it is polar means it will be having both positive and the negative voltages, both, and it is returning to 0. So this is, so returning to 0 means whenever it is going to do the transition here, it is going to return to 0 into one data element. So this is the 0 is the data element. It will be going for half of the cycle, it will be negative, then returning to 0, then again it will be going with respect to the next signal. So here it is like 0 is represented by negative and 1 is represented by positive value or positive voltage level, or negative, these are like voltage levels. In between one data element, the pulse or the signal will be going to the 0 level, and then this is the 0 level. So from, you can just see this is the negative side and this is the positive side. It started from here going to the 0 and then with respect to here. Okay, likewise. So 0 is represented by negative, starting with negative, then going to 0, then again 1 is there, so it will be going to high, then again returning to 0, returning to 0. So in the same bit element or the data element, it is coming or to 0 or returning to 0. Then again it is 0, so it will be coming from here, like up to here. Then again it is 0, so it will be going down, then returning to 0. So each time it is returning to 0. So if it is returning to 0, that means it is going to basically average the DC. So now if we consider the DC level here, so average you can take different values. If it is negative, then it is 0, positive. So if you take the average of the signals, average of signal level is equivalent to DC component. So here the DC component will be coming out to be like 0. So if it is DC component is coming out to be 0, that means the most of the frequencies or at 0 frequency, the component's power of the signal will not be highest. So because DC component is 0, so at 0 frequency there will be 0 power. This is what the basic objective. So if this is the case, now this can be transmitted through a band pass channel. It can be transmitted through a band pass channel now. So in case of polar returning to 0 scheme, the R is defined by 1 by 2. So means for sending one bit of data or one data element, we need two constant levels. So two signal levels are being used, or two signal elements are being used. So 1 by 2 is the R, and as signal rate is equals to data rate, or whatever the data is there, the signal rate will be the same. Next we will see is in polar only the biphase. So in biphase, this is of two types. So one is Manchester Another one is called the differential Manchester. This is the first one. This is the second one. So this is first and this is second. So what is the meaning of the first and second? We will just see. Yes, one more thing. In the previous case, it is like here it is not constant, it is going to 0. So it is returning to 0. In terms of implementation, it is complex. It is complex to implement basically. But there is no DC component. So DC component problem is not there. And also it is DC component problem is not there. And also in terms of the bandwidth, better bandwidth utilization, the moderate bandwidth will be there because here two signal levels are there. So bandwidth requirement in terms of the requirement, it is going to be high. So there is no DC component level. And in terms of complexity, it is simple. And in terms of the error correction, there is no error correction. Bandwidth requirement is somewhat higher. The next one is Manchester and differential Manchester schemes. So in case of Manchester schemes, basically here it is polar biphase. So it is polar schemes. First of all, polar in the sense it will be going towards positive and negative side both. And in Manchester, it is considered as a combination of both RZ scheme plus NRZL. So NRZL and RZ scheme. So both schemes is basically utilized here. So first of all, it will be defining the levels. So if it is 0 means, so for 0 is given by this pulse. So it is from high to low. It is going to be high to low. If it is 1 means it is low to high. So whenever there is 0, it is going from high to low. Then again it is 1, then low to high. Then again it is 0, then high to low. Again it is 0, so it will be going to high, then high to low. So this is what the Manchester scheme is there. That is, it is basically considered as having the properties of the RZ and NRZL. So in case of RZ, also it is having the property of having synchronization. So whenever it is going from high to level 0 or low to level 0 or positive side to level 0, so whenever returns to 0, this returns to 0 is basically used for synchronization. So this polar is having synchronization, polar RZ. So the same, this Manchester is going to have the advantage of the synchronization, as well as it is having the DC component 0, and also it is having synchronization. So no DC component synchronization is there. In terms of S average, signal rate is basically n. In terms of bandwidth, you can just see. So here bandwidth is also like somewhat less. Okay, bandwidth requirement is also moderate, and signal rate is basically equals to n. So you can just see in NRZ, average NRZ, basically it was n by 2. So if it is signal rate is less, that is more suitable. But here the signal rate is high. So this is one of the disadvantages in case of the Manchester and also in differential Manchester. Okay, so it will be having double the signal rate basically. And in terms of bandwidth here, so having higher bandwidth, or basically it is 2 times the NRZ. The bandwidth is there. Okay, so in case of the Manchester and differential Manchester. Next one is the differential Manchester. So this differential Manchester is considered like RZ plus having the properties of NRZ I. I means inversion. So it is going to be returned to 0 and NRZ I. So these properties are there into the differential Manchester. How it is basically encoded. So here again, it is like starting with the positive. So starting with here positive 1. So then if it is 0, so its meaning is if next bit is 0, then there is an inversion. There is an inversion needs to take place. So if for 0, it should be likewise in the Manchester case. But here, instead of inversion, because it is 0, so it will be going to inversion. Inversion means it needs to invert this. So instead of high to low, it is low to high now. Then it will be coming at this position. At this position, it will be checking next bit is 1. So if next bit is 1, then there will be no inversion. Okay, so there will be no inversion. Means whatever is the level previously, the same level will be coming out. So if it is a positive, so it will be positive again. Then for half of the time period, it will be positive, and half of the period it will be negative. Then again at this position, next bit is 0. So if next bit is 0, then there will be inversion. Inversion means if it is coming out to be low or the negative, so negative will be inverted. It will be positive now. So then half of the cycle positive, then half of the cycle negative. Again, the next bit is 0. So next bit is 0 because this is 0. So this is again going to be invert. So this is going to be invert. So once inverted, likewise this at this position, we will again check next bit is 1. So if it next bit is 1, no inversion. No inversion means it was negative. Again, it will keep on negative for half. Then for half it is positive. So likewise, this is differential Manchester. So in Manchester and differential Manchester encoding, the transition at the middle of the bit is used for synchronization. So synchronization, because in case of RZ, we were having the synchronization, return to 0. Transition between the single data element, this transition is basically utilized for synchronization. Whenever there is transition, this transition is used for synchronization. The next is the minimum bandwidth of the Manchester and differential Manchester is 2 times that of the NRZ. So signal rate is basically n by 2 in case of NRZ scheme, but here it is n in Manchester and differential Manchester. This is the signal rate, but the signal rate is basically, we can call it like bandwidth, is directly proportional to the signal rate. So it is considered like the minimum bandwidth is considered as the S. Okay. So if we talk about the minimum bandwidth, so in that case, if we compare these two, so it is saying like the minimum bandwidth in Manchester and differential Manchester is 2 times the NRZ. So this is the NRZ. If it 2 times the NRZ is there, so bandwidth is higher in case of Manchester and differential. So our motive is we should be having higher data rate. Our goal before doing this encoding is, the goal is like we should be having high data rate, we should be having high data rate and low bandwidth requirement. So these are the two goals while doing this line coding basically. So high data rate means we should be able to send higher data per second, or we need to increase the number of bits that we are sending per signal that we are sending. So into one signal element, what number of bits we are sending, that should be increased, so we can have the high data rate. After the polar, there comes the bipolar. So in bipolar, we will be using the positive, 0 and negative levels. The 3 voltage levels are basically used into the bipolar. So into the bipolar, we are having 2 different techniques basically. These 2 techniques are called like AMI and pseudo ternary. So AMI and pseudo ternary. So this AMI stands for alternate mask inversion. So here mask is basically considered, can be represented by like 1. So whenever there is 1, we are going to have this, another name is like alternate 1 inversion. So whenever there is 1, alternate ones will be inverted. So this is basically used to reduce the DC component. Okay, that means if positive and negative components will be there, so it will be nullified. So for that it is used basically the alternate 1 inversions are used. So it is alternate mask inversion. So AMI technique is there. Another one is pseudo ternary. So we will just see like what is these 2 techniques. So here in AMI, so 0 will be represented by 0, 1 will be represented by 1 or high voltage, or 0 will be by low voltage. So 0 is low, 1 is high with alternate inversion. So what it is meaning is, whenever 1 is there, first 1 is there, so it will be high. Then 0, it will be 0 level, 0, 0 level. Next one, this is the first one, this is the second one, this is the first. So first is represented by high, then second will be inverted. So this is alternate mask inversion or alternate 1 inversion. So first one is high, then next one will be low. Then suppose next one comes, that will be high. Then third and fourth will come again, the low or the negative one. So this is the EMI scheme. So that is represented by the bipolar. So bipolar means 3 levels will be there, positive, negative and 0. So here 0, positive and negative. Next one is pseudo ternary. So into the pseudo ternary, it is represented by like high is there. So 0 is high, then it comes 1. So 1 comes 0. So it is just the opposite of AMI. That means whenever there is So if it is 1, so it is represented by 0. So again here 0 is there. So 0 is being represented by like not low, it is 0. 0 is represented by 0. Here in the pseudo ternary, 1 will be represented by 0. So whenever there will be 1, it will be represented by 0. And 0 will be represented by or low, or we can call it like high with alternate inversion. So high, then alternate inversions will be there, or low, high or low. So whenever there is 0, the first is represented by high. Then 1 will be represented by 0. Then again 0. So this is the first 0. This is the second 0. The second 0 will be represented by its alternate. So it's inversion. So high, it will be low or negative. If it is positive, it is negative. Then next 0 is coming. That means it is third one. So if it is third 0, so third 0 will be inversion to this one. So it is negative, so it will be positive. So again, next, this is the fourth. So fourth 0 is there. So it was third 0 was high, then fourth 0 will be low. Otherwise, whatever ones will be there, ones will be 0 only. So this is the pseudo ternary. In the pseudo ternary, average sample rate is n by 2, similar to the NRZ, and its bandwidth, in terms of bandwidth requirement, you can just see here most of the power is basically at in between 0 and 1. So it is like DC component here is 0 basically. So here there is no DC component because it is in between 0 and 1. And if we talk about the signal rate is similar to the signal rate of NRZ. NRZ is having the same signal rate, but in NRZ we are having the DC component. So if DC component is there, that means most of its energy is basically near to the 0 frequency. So for transmission, there will be a poor quality of transmission. That's why this bipolar schemes will be preferred over the NRZ.